First, let's talk about how you make the web faster and what goes into that. There are a lot of things that are involved in user-perceived latencies, all the networks you build, of course, but other things. An important one is the increasing use of TLS. For example, now Google, and in particular YouTube, is almost all secure. And so that's a big part of user-perceived latency. So what have we done? We built a huge CDN. We have one of the largest CDNs in the world. We offer Google Global Cache to those who want to install it and get closer to their users. And we generally have a huge network that we've spent a huge amount of money building out just to make the user experience faster. Excellent. So we've also made our own browser. We've done Chrome, which has had many innovative things built into it, one of which became HTTP 2. So we're really trying to advance the space, and do anything we can to both make the web more secure and faster. But what else? What's in the middle? Well, there's transport, traditionally TCP. And we've done a lot of work with TCP. We have some of the best and brightest working on it already. But we wonder, what else could we do? So the question is, what is QUIC? It's a reliable multiplex transport over UDP. It's always encrypted. It reduces latency. It runs in user space, so we can upgrade it quickly and deploy it quickly. And it's open source. So where does it fit on all these stacks? So it subsumes some of the things that TLS 1.2 does, pretty much all of them, the handshake, as well as the cryptography. It adds some of the things that HTTP 2 do, such as multi-streaming. And it also does things like congestion control from TCP and loss recovery. How do you make sure QUIC works well? A very important question. So 443 needs to be open, otherwise it won't work at all. UDP rate limiters are definitely bad. Any other type of differential QoS tends to be bad. And reasonable stateful firewall and NAT timeouts. So we did a variety of experimentation and found that 30 seconds was a very conservative timeout value, and that very, very few NATs expired in less than 30 seconds. And so that's what we've chosen. But we need a certain amount of time to actually keep the connection open. And we need reasonable load balancing. So as we scale up QUIC, we don't want to have any issues where suddenly we end up all on one port of your router, and other issues where things are not distributed evenly. Let's talk about congestion control and reliability. So QUIC is reliable, just like TCP. It incorporates all the best practices and really builds on years and years of learning with TCP. Even though TCP hasn't really evolved very much on the wire over time, it's really evolved a lot in terms of the techniques used to make sure that TCP works really, really well. So it incorporates QUIC, so it's fair with existing TCP implementations, FAC, TLP, and all the most modern RFCs, as well as some that aren't even full RFCs yet. But it also adds some signaling improvements that can't be done in TCP. For example, retransmissions come with a new sequence number. So because of that, you have no disambiguity when you're retransmitting a packet. You have very good RTT information, you know exactly what happened on the connection. And there's a lot of code in TCP to try to do disambiguation. It makes the code base and the kernel a lot more complicated. This is also a good time to call out the fact that there are a lot of things people would like to add to TCP and kind of improvements that they would like to make. But probably the most complex and most important one that's ever been added is selective acknowledgement, or the SAC option. And that's been around for about 20 years. And it's now, the last metrics I looked at, about 90% deployed. So even really, really compelling improvements to TCP take a very, very long time. And they're very hard to experiment with because of that, because you really don't know how well it performs until you deploy it at scale. So we have a lot more other flexibility going forward. We can change how the receiver acknowledges data, for example, either to get more information or to make the network more efficient. So it's important to talk about faster connection establishment. This is a core feature of QUIC that was designed in from the ground up. We combined the handshake for the connection with the handshake for security all in one. And in the best case, it only takes it takes 0 round trips in the sense that it is immediately established and you can send a request on the first flight. So with TCP, it's typically 1. With TCP plus TLS, it's either 2 or 3, depending on whether you can resume the connection. And in QUIC, 75% of the time, it's 0, and 25% of the time, it's 1. So the worst case scenario is you have to do a full round trip. And that, of course, relies on you having talked to the server before, but at least in Google's case, most people have talked to google.com before. Oh. So it's always encrypted. It's very comparable to TLS and actually uses 2 of the ciphers that TLS supports. Actually, it supports the only 2 that I believe are widely considered to be the most secure. It has IP spoofing protection. So it has proof of source address token, even though it's 0 RTT. It does have proof of source address token. And it also inspired TLS 1.3's 0 RTT handshake. So, already we're seeing interest in adopting this and moving some of the technology we've developed in QUIC into other forums and to be used for TCP as well. So how well does it work? So we spend a lot of time measuring performance and making sure that we really know how well it works in one. We do controlled experiments. We gather client-side data. We gather server-side data. We make sure they match up. We gather all kinds of error information, anything that could possibly go wrong. And we also do a lot of fine-grained analysis. So we almost always do analysis by AS. We also do analysis by location, like serving location. And we'll do analysis by operating system, anything else. So any way we can slice and dice it, we'll look at the data. And we also give you a view into it on peering.google.com. So as a recent feature, we now have added a lot more QUIC-centric information there. So how well does it work on Google properties? So on average, it's 5% faster. It's 1 second faster for web search at the 99th percentile. Now, 5% doesn't sound huge in some ways, but we do incredible things to optimize everything we possibly can. So the fact that there's anything left on the table is sort of amazing. And also I want to emphasize, as I said before, this is making the cost of doing a secure connection really kind of nothing from a user latency perspective, which is a really critical improvement. So also improves YouTube quality of experience, 30% fewer rebuffers, which is a huge difference. And we have a lot more improvements to come. We're only at the beginning. Forward error correction, bandwidth resumption, much more. So 0 RTT is one of the big ones in terms of where all the improvements come. Over half of the latency improvements come from that one thing at the moment. It's also the feature we sort of designed the protocol around to work really well, and we've invested a huge amount of time in. We also have better loss recovery. So those of you who are familiar with TCP, usually around 30% of retransmits are timer-based. Those introduce a lot of latency to, from the end user's perspective. QUIC has almost 10 times fewer timer-based retransmits than TCP in a typical case. And this really comes off as, much, much better tail latency. And that's one of the things that contributes to the fewer rebuffers. And there are other smaller things, head-of-line blocking. Because we're using UDP, we can deliver data out of order, more efficient framing, and some other minor tweaks. So when is it deployed? So it started in 2013 in Chrome Canary. 2014 was when it hit Chrome Stable. And currently we're in the process of ramping it up over the course of this year and have really started around January of this year. So what are we doing to protect users and your networks? On the client side, if UDP is blocked, we just fall back. It's just like IPv6, happy eyeball sort of race. And the user is never the wiser. If the path MTU is too small, because we currently use around a 1350 byte packet, then the handshake will fail. And again, the user will be none the wiser. And what if the client doesn't want to use QUIC? They have a problem, they have a policy, it doesn't matter what the reason. They can disable it in Chrome, or you can do a policy-wide disable to disable it as a site administrator across your site. Sometimes client-side protection is not quite enough. So as a last resort, Google will disable it QUIC on a per ASN basis. This is kind of the thing we'd like to do the least, but occasionally there are issues that we just can't resolve on the client side and can't detect easily on the client side. So why would we disable QUIC? Usually we get lots of indications that quality of experience, commonly YouTube, is hugely degraded for that network. Commonly it's due to UDP rate limiting, virtually always, actually. And in the worst case scenario, we rely on end user reports to give us indications of problems. So QUIC on your network. On peering.google.com/QUIC-FAQ, there's some excellent information on QUIC. And there is also a link to how to sign up for a peering account so you can see all of this information. So there's a traffic summary about how much of the data flowing into your network is QUIC. There's a profile of how it varies over the course of the day. And it also will tell you whether your network is one of the networks we found is not QUIC friendly. So is either blocking UDP or is highly filtering UDP. So in terms of debugging, the best tool is Chrome. Chrome itself has an excellent net internals pane. It's one of the standard tabs that's even in Chrome stable. And that's where we get the most detailed bug reports of any issues that we find. It allows you to see into the QUIC frames themselves, so you can see what's the data, what's an acknowledgement, the connection establishment, what all the handshake parameters are. It really gives you a very, very detailed view into the QUIC protocol. And if you're just curious and want to take a look, then fire it up and it'll be there. There's also a Wireshark plugin that'll identify QUIC, identify the flow identifier called the connection ID, identify packets by sequence number. So again, sequence numbers don't repeat in QUIC and they start at 1, so a little bit different from TCP, but conceptually similar. But it'll give you an idea of how big a flow is, how long it lasts for, and all of that information. I'll also tell you the QUIC version. So we're currently on actually version 25, not version 24. And we've been slowing down our version iteration a fair amount, but it is relatively rapidly iterating compared to most transports. So what's next? Coming in the future, many people have asked, when are we going to do forward error correction? And the answer is, well, we're experimenting with it, but making it work really, really well is hard. Connection mobility. So, there's a lot of interest in migrating from cell to Wi-Fi and back and forth. And we're starting to work on that now as well. Multipath is a natural follow-on to that, particularly for mobile devices. And more improvements in congestion control. Originally in QUIC, we kind of thought, we're going to completely rewrite TCP. And it turns out, doing an entirely new transport is enough of a project in and of itself that you might as well keep a few things the same. And I think the choice to stick with QUIC for now was a very wise choice. So, open source. We have a server that's in Chromium that you can play with. It is not intended to be ultra high performance, but it certainly is correct, and it certainly will give you an idea of what you can expect out of QUIC. We're working to support QUIC in Apache Traffic Server. No actual ETA on that, but definitely we hope that it'll happen sometime in the not too distant future. And we have some open source Chromium climate libraries for both desktop and for mobile. And Google Chrome and some various Google mobile apps are the main people who actually use QUIC. But yes, we are talking about the other browsers as well for the future. So QUIC has been presented at the IATF back in 2013 as an initial idea. It's changed quite a bit since then, but the concepts are still the same. Most recently at the IATF in Dallas, the QUIC crypto was presented. This was very much timely because now that TLS 1.3 is kind of starting to move along, there was really a lot of people had questions about how QUIC crypto related to TLS 1.3. And kind of the answer is TLS 1.3 in many ways is going to end up subsuming QUIC crypto as a profile inside of it. There's going to be an updated presentation this summer in Prague. And we have ongoing work, as I mentioned, to kind of make sure that QUIC's zero RTT handshake kind of merges with TLS 1.3 so we can eventually move directly to TLS 1.3 for QUIC. So in review, it's reliable, it's multiplexed, it runs over UDP, it's always encrypted, has optional forward error correction, has a rapidly evolving implementation, and it's open source. But most importantly, the one thing I skipped over, of course, intentionally, was that is designed to be lower latency for users. It's really designed to improve user experience, make the user experience more reliable, faster, and just generally make the web work better. So how do we get safe passage of QUIC? Basically treat UDP like TCP. Open 443, don't rate limit it. Make sure that the QoS is set up reasonably. As I said, reasonable firewall and NAT rules. And have your traffic distributed evenly. All right, and as I mentioned before, peering.google.com has more information about QUIC, as well as how you can get more information about your AS if you have one. Questions?
Phil Rosenthal from IS Prime.
Yeah.
So I think it's actually wonderful work to improve on HTTP. It's a long time coming. One of the features that is very clearly core to it is always encrypted, but there is a downside to that, which I think even in the best case scenario, when you're encrypting data, you're using, say, 40% more computation cycles to do that, and there is a cost to that.
Right.
In some cases, that encryption is obviously valuable. I want my bank to be encrypted, but I may not necessarily care that some video streams are encrypted. So if it's going to be something for the internet as a whole that we encourage everyone to use, is there any thoughts to to allowing at some point an unencrypted version? And if not, what do you say to the all of the years of effort towards zero copy that it seems to be now throwing away and going the opposite extreme?
No, that's a reasonable question. So one thing is, at least based on my understanding, and this is talking to the security folks at Google and as well as at Netflix actually, that some recent work to make encryption faster has really helped. And so I think the 40% number is a little bit high based on my experience, because, for example, Netflix added an option to do it was encryption in the kernel. So you could write a file directly to the kernel and it would encrypt it for you, and it was extremely fast. But in general, I think, at least for Google, the right choice is to always encrypt things as much as possible. For everyone else, I would encourage them to kind of tend to do so as well. But it does incur some CPU costs. So I guess the answer is I tend to think it's worth it. But I don't know if you. Oh, this is Brian Rogan, by the way.
Hi. Yeah, I think that's definitely, your observation is definitely what we found, is that in deploying crypto widely, right, so now something north of 70% of all traffic from Google by volume is encrypted. It's obviously a big priority for us as a company. We actually found the primary CPU cost has generally been copy overhead, not actually crypto, right? It's quite efficient, especially symmetric ciphers on modern processors, right? But I think for us, and a big part of QUIC is kind of that, is taking that payload and kind of bringing back end-to-endedness to it, right? So, I mean, the encryption serves a lot of purposes, but from our perspective, I think it's an important feature of the protocol.
Yeah, I should also add, to go back to the work with Speedy, the feeling about Speedy was that if it wasn't encrypted, that it would never get through the network. And I think there's also a little bit of a fear of that for QUIC as well, is that if it's not encrypted, that there's going to be a few more issues with tampering and other such things. So there's definitely a concern. But yeah.
Thank you.
I think, yeah.
Sure. Chris Luke, Comcast. So some of us were just looking at the stats for QUIC on our network, which is great. Their web page is really pretty. Good job on that. But the number was something like 5%. And given Chrome's penetration, that seemed a bit low to me. Can you explain what some of that discrepancy might be?
So I think I can speak to the deployment right now. So we deployed QUIC quite widely differently across different Google services, right? And so, so Ian works on QUIC, the protocol. I work on content delivery at Google and how we scale that delivery, right? And basically what we're doing is scaling our different products at different rates, right? So, I mean, the QUIC rollout on our side is not complete, right? It's farther along for some products than others, and so we're ramping up, some of our biggest sources of traffic now and over the next few months.
Sure.
I don't know.
I was just kind of curious what the breakdown is in terms of if you've had experience with QUIC operating over what I'd call like middle box heavy environments, or in mobile versus kind of standard wireline deployments. Do you how does the fallback work? I mean, how often do you fall back when you're traversing to kind of middle box environments?
Sure. So we found that overall, it works, or QUIC, it's possible to use QUIC something like 95% of the time. That's pretty similar to I think the numbers that the WebRTC folks have found as well. Maybe theirs are a little bit higher, but and so in general, it almost always works. We haven't found any issues that are particular to mobile environments at all so far. The hardest part about mobile so far has actually been computation. Things like not only the crypto that was mentioned earlier, but just generally, computation is much more limited on mobile. So that's actually been a much bigger issue. And yeah. Hey.
Hi, Chris Woodfield, Twitter. You mentioned the recommendations for reasonable timeouts for stateful devices. I think 30 seconds is what you said for UDP.
Yeah, I think the most common number we found was either 60 or some number much more than 60, but we used 30 because we found essentially no devices that seemed to time out before that.
Okay. My question is there anything in the protocol today or plans to put in the protocol the equivalent of a closed message, the equivalent of a TCP fin or RS reset, so that a stateful device could watch for that and clear out the session table sooner?
Yes, there is actually discussion of that, and currently the close is encrypted, so you can't really watch it. And I think Jana might be wanting to answer that question right now. He's right behind you. He's also a team member.
Jana Google. So yes, it'll be very useful to have, and there's actually a fair amount of discussion at the IETF even about having UDP-based transports show a SYN and a FIN bit, but of course it opens up the Pandora's box of reset attacks and various other things. One of QUIC's big strengths is that the entire header, QUIC header, is in fact authenticated by the receiver, which allows us to thwart any sort of injection attacks, and this would open the door to that. But of course it's a conversation that can be had, but in the face of possible attacks, you kind of have to infer things without reading simply whatever bit is sent to you. So the conversation goes there.
Thank you. Yeah. I think you were next. I'm not sure.
I'm Vince from Zendesk. So I have no questions about the performance and how cool the protocol is. My question is more about, I know that Google is proposing this as an open standard in IETF, right? And do you guys see the community in a medium long term migrating to serve HTTP traffic by QUIC, or maybe all the knowledge and experience from this protocol being brought to TCP in a long term or something like that?
I think personally I see it as both, right? As much as possible, we would love to do things that bring improvements back to TCP. That's definitely a huge win. But I tend to think that we're going to end up wanting to deploy QUIC as well fairly widely, because we are going to be able to do things that are just not going to be able to be deployed in a reasonable time frame for TCP. But hard to know how it'll play out.
Thank you.
Hi, Armin Babikian, Switch.co. I've got a question about the port 443 requirement that you guys have for QUIC. Does that mean that a single server, listening on a single IP address, has to have the entire, all the services that it's trying to give, all the services it's trying to provide, hosted on a single port on the machine, or do you guys plan to generalize that or relax that requirement?
So in terms of, you're talking about in terms of serving architecture?
Yes.
So it doesn't really have to be 443 semantic. I mean, you could certainly configure it yourself and use it on any port you want. But in the context of doing HTTPS traffic, The goal is to use 443. So if QUIC were used for WebRTC or something else, then it would be on a different port.
Sort of a follow-on to, with respect to QUIC and WebRTC, is that supported at the moment, or?
It is not supported. There's definitely hope to make that happen at some point, but it's who knows when that'll happen. So,
Okay.
yeah. Sorry, I think you were. I thought.
Spencer Dawkins, for the purpose of this conversation, Transport Area Director at the IETF. Thank you guys for bringing the work that you brought to the IETF so far. There are a lot of things about QUIC that I'm excited about, both about feedback to TCP and other transport protocols, and in its own case for deployment. Having said that, have I seen a BOF request from you guys?
That's a
Jana
question.
Yangar, no, you have not. And that's because we haven't sent it yet.
I look forward to one with bated breath. And actually, a couple people from Google have told me one is coming, which is why I asked. But just wanted to make sure. Like I say, I look forward to this with interest. Thank you.
Yeah, that process I leave up to Jana.
I'll just say that there may be a BARBOF request coming up very, very soon.
Do the right thing.
Just a quick question. You said this is open source, but I saw no pointers to any place where we can look at the source for this. Is this sort of open in a theoretical sense, or do you actually have a code repository we can look at?
It is actually all in Chromium. So I think if you go to the FAQ and there should be a Chromium link for the Chromium explanation of kind of this is QUIC and here are some detailed design docs. There's like a crypto doc and a variety
You
of other
don't have
things.
like a separate library we can grab? You have to grab the whole freaking Chrome?
So, yes, that is really annoying right now. I'm going to just acknowledge that right now. There is actually an external team, I believe, working on trying to librarize it, and we've talked about how to make it easier many times. So currently it's hard, but there is I know an ongoing effort to try to librarize it as well.
Thank you.
Yeah. Yeah.
I haven't really had time to check yet because I just basically got it working, but you mentioned that your close message is encrypted. Are you working at all with the SSL session key, or are there plans to, as a method of decryption?
I am not familiar with that. I don't know if John or anyone else from Google can comment. I think the answer is no, but I also did not write all the crypto stack. That was mostly Adam Langley and a few others.
Fair enough. Thanks.
Great. Thank you very much.